recent progress for the fourth installment of recent progress in K-stability of Fano varieties. Thank you, Yuchen.
Okay, thank you very much for the introduction and the invitation again. So today I will continue the lecture series on K-stability of Fano varieties with a focus on higher rank finite generation. So as Ziquan introduced the higher rank finite generation last time and started the first part of the proof, so I will continue from where he left last time on the proof of this conjecture. So first of all, let us just recall the statement. So I have a Fano variety X, which has KLT singularities, in other words, Q Fano, and I assume that the delta invariant of my Fano variety is at most 1. So this just means that my X is not uniformly K-stable. And then I assume that this delta invariant is computed by a valuation V, and actually the existence of such valuation is proved by Bloom-Janssen and later different method by Bloom, myself, and Chenyang Xu. So then the statement of the higher rank finite generation is the graded ring of R, which is the anti-canonical ring of my Fano variety with respect to this valuation V is finitely generated. And this will give us an optimal destabilization of the Fano variety. Okay, so let us just recall some of the previous results. So first, we know that the valuation V is actually has some nice geometric property. So it is a quasi-monomial valuation, and moreover, it is a log canonical place of a Q complement of your Fano variety. So this is shown in the previous work by Harold Bloom, myself, and Chenyang Xu. And to put this more in concrete forms, this just means that I can pick a log resolution Y with a divisor simple normal crossing E to X, such that my valuation V is monomial on this model YE. So this just means that I can write my E as the sum of R divisors, EI, and then you can assume that they intersect transversally at some center, which is of codimension R. And I have a weight vector alpha, which is real coefficient, such that my V locally just represent as this monomial valuation. My V alpha, if I restrict evaluate on the divisor EI, then I just get the i's component alpha I. And I also assume that all these alpha i's, they are rational linearly independent. So that you are basically finding the minimal linear span of these vectors. Okay. And then last time, Ziquan introduced this so-called theorem A, which is an intermediate result transforming the finite generation of the gradient algebra into some other properties. And eventually, we will transform into a property that birational geometric tools can be applied. So again, here my assumption is my V is an LC place, so quasi-monomial LC place of a Q complement, where this alpha here just represents the weight vector. And the following are equivalent. So the first condition is this finite generation of the graded ring. And the second condition is this linearity of the S invariant. So here my beta is inside a neighborhood of alpha. So you think about alpha as a vector in the R-dimensional Euclidean space. And then you perturb the weight a little bit. And then you still have a V beta being LC place of a Q complement. And the statement just says that the S invariant is linear in a neighborhood of alpha. So we know that last time Ziquan explained the reason why these two are equivalent. So basically, you have a concavity result on S invariant using the compatible divisor trick. And then if a concave function is linear, then somehow you can interpolate their corresponding filtrations in the sense that you know that the graded ring of them have a certain degeneration properties. And today we will actually focus on the third one, which is saying that if I take the approach of this graded ring with respect to V beta for a small perturbation of alpha to a rational vector beta, then this proj is actually bounded for any beta in this small neighborhood that is also rational. So the boundedness is certainly a very nice birational geometric condition, and it implies the linearity of S and hence the finite generation. Okay, so what is X beta here? Actually, because my beta here is a rational vector, your X beta is a central fiber of some test configuration induced by this valuation V beta. So somehow X beta is, you can think about them as some degeneration of my original Fano variety X, and we want to show that they are bounded. Okay, and to transform boundedness into some more familiar condition of singularities, then we have this boundedness result due to Chenyang, and later with a different proof by Xu and Zhuang, which says that it suffices to just bound the alpha invariant of X beta from below for some positive constant alpha 0 for this beta sufficiently close to U. And the reason here is that we actually have, so X degenerates to X beta. This is the special test configuration induced by V beta, sorry, maybe weakly special to start with. So therefore, you know that this degeneration is Kähler-Einstein, so the volume are the same. So maybe I denote this by V. So the theorem that Jiang proved is that if your Q Fano varieties have a lower bound on the alpha invariant and also a lower bound on the volume, then they're bounded. And Jiang's argument is like a generalization or application of Bierkar's proof in the BAB conjecture. And later on, Xu and Zhuang gave another proof based on the Bettiroff conjecture proved by Hayken, McKernan, and Xu. But anyway, we somehow just transform this boundedness question into a statement about the alpha invariant of the central file. Okay, is there any question? Okay, so now I want to go further from this point. So we know that not every LC place of a Q complement satisfy finite generation, right? So last time Zichuan mentioned some example where you have a log canonical place of the nodal cubic curve on P2, where it is not finitely generated, has finitely generated graded algebra. So therefore, we want to put some restriction. So we want certain restrictions on the Q complement. And one thing that we start from is this condition, to analyze this condition that alpha invariant has a lower bound. So you know that the V beta is some valuation on your Fano variety X, and it induces this degeneration X to X beta, but we want to transform this alpha condition on X beta to something about the complement, where V beta lies in the LC places. Okay, so this starts from a lemma, which is not so hard, but actually very useful. So suppose I have a divisorial valuation. So let's say order of vanishing E. So this E is different from the E earlier. So suppose this is a divisorial valuation on X that induces, let's say, a weakly special test configuration, so TC, where it degenerates my Fano variety X into the central fiber X0. So this is equivalent to say that my E is an LC place, let's say a divisorial LC place of some Q complement. So weakly special just means that my X0 here is a semi-log canonical. And then the statement of the lemma says that my alpha invariant of the central fiber is bigger than some positive constant alpha 0, if and only if I can actually find some complement which contains any given divisor in the anti-canonical linear system. So if for any divisor D in this minus kx Q linear system, you can find a Q complement gamma, which is bigger or equal to alpha 0 times D, such that E is an LC place of X gamma. So in other words, this lemma just says that if I want to bound my alpha invariant from below, then you have lots of freedom to choose the complement whose LC place contains the given divisor. So this basically just gives us a lot of flexibility in finding the complements. And this will be very important in proving the finite generation. Okay, so let us see, give a quick idea of how the proof would go. So indeed, the proof is also not so hard. It's just some translation of this this weakly special test configuration with the LC places of complements. Okay, so first of all, we want to show that if alpha invariant has a lower bound, then you can find such a Q complement. So which is the forward direction. So here we know that suppose I have alpha of X0 is bigger or equal to alpha 0, is bigger than 0, then any divisor D, I can look at the degeneration to the central fiber, which is the divisor D0, and you know that because the family is the Q-Gorenstein, where the central fiber is also Fano, my D0 is also Q linearly equivalent to minus KX0. So I know that hence, from the definition of alpha invariant, I know that X alpha 0 D0, sorry, this should be X0. This is semi-log canonical. And in fact, you can, because the alpha invariant is positive, you can show that it's always KLT. So it's indeed a log canonical. Okay, so now I have a weakly special degeneration of X and alpha 0D, right? You can see that this is the induced degeneration of the pair, where this is essentially a log Fano pair, and the central fiber is semi-log canonical, so which means this is weakly special. Hence, we use this this criteria proved by Bloom, Xu, and myself. So this just says that E is an LC place of a Q complement gamma of the pair X alpha 0D. Right, because here I'm basically just including this divisor, some fixed multiple of this divisor, you still get something semi-log canonical in the central fiber. So this means that from BLX, we prove that weakly special degeneration is one-to-one corresponding to the LC place of Q complements. So now I apply this to this new log Fano pair. This implies that my gamma is actually bigger than alpha 0D. Okay, so this proves one direction. And for the other direction, we know that suppose you have this condition that gamma is always bigger or equal to alpha 0D. So what this means is just, again, using BLX. This just means that that E induces a weakly special test configuration for this pair X alpha 0D, where my D is arbitrary in this Q linear system. Right, because you see that the assumption here is I can find this Q complement gamma, which is bigger than alpha 0D. So in other words, if I put the pair X alpha 0D, then your E is an LC place of complement of this new pair. So therefore, this induces weakly special test configuration of X alpha 0D. And this again implies that that I actually have X alpha, sorry, X0 alpha 0 D0 is so let's say semi-log canonical or log canonical. Okay, maybe I put a semi-log canonical here. But then you can see that my D0 is the degeneration of my divisor D. So it is always GM equivariant. So since D degenerate to D0 in this test configuration, we know that D0 is GM equivariant. But on the other hand, because this degeneration is Q-Gorenstein, you can show that the anti-canonical divisors or plural anti-canonical divisor is flat in this family. So every GM invariant divisor D0 on X0 appears this way or arises this way. Then you can use the fact that log canonical threshold is lower semi-continuous, so that I know that alpha X0 is indeed the infimum of log canonical threshold of X arbitrary divisor D0, but now I can restrict my D0 to be GM equivariant. So therefore, this implies that this is always bigger than alpha 0. Okay, so then the lemma is proved. Okay, any questions? So let's just recall the statement of the lemma. So the lemma just says that in order for this degeneration induced by weakly special divisor or LC place of a complement have a lower bound on the alpha invariant, then what you need is just the flexibility of choosing the complement, where you can actually require that the complement contains a fixed multiple of any anti-canonical divisor or Q anti-canonical divisor. So, so this sort of gives us a hint on putting some extra, stronger constraint on the complement where my delta minimizer would satisfy. So now is a good time to introduce this concept called the special complements. So the definition seems a little bit technical, but actually it is designed to satisfy this flexibility of choosing a certain complement. Okay, so let's give the definition. So we say that suppose X again is a Q Fano variety, and I have a log resolution YE. So this is a log resolution of X, and we say that gamma is a special complement on X with respect to this log resolution if the following condition holds, which is also a simple condition, that's the pullback for the strict transform, which I call it gamma Y. So suppose this map is pi, then I just take the strict transform of gamma. Then this is bigger than some divisor G, where G is there exists some divisor, which is effective and ample on Y. And I also require that the G avoid any stratum of E. So in some sense, my G here is just some ample divisor, just chosen in a general way, so that it does not pass through all these intersection stratum of my simple normal crossing divisor E. Okay, so in particular, because I know that my valuation V is a monomial in this model YE, so therefore the center of V will be one of the strata. So this forces my gamma to contain a divisor G, where G is just avoid the center of my valuation. So therefore you can always subtract this divisor G from gamma, where even after subtraction, so you get something which is smaller than complement, but still has my valuation being an LC place. So we say that V is a so-called monomial LC place of a special complement gamma if V just lies inside the quasi-monomial valuations and intersect the space of all LC places. So I just use this acronym LCP to denote the LC places of this pair. Okay, and because of this G is ample, so you can see that you can always assume that G is bigger than some small multiple of some anti-canonical divisor on X after you push forward. So this would imply that that my V is an LC place of this pair X, and I have gamma, but then I can subtract this push forward of G. Okay, so now you have a divisor boundary divisor gamma minus some push forward of ample guy, which is certainly smaller than the anti-canonical divisor. Meanwhile, your V is still an LC place. So this gives you some room to add in this extra divisor D, so that I want to satisfy this alpha always have a lower bound. Okay, are there any questions? So let me just comment. So providing add in some small multiple of D. Okay, so this is the concept of special complements, where I just require my complement after you look at the strict transform on log resolution is bigger than some ample divisor, avoiding the stratum of E. Okay, so now I will reduce proving the finite generation into two statements. So the first one is also introduced by Ziquan last time. So we call it Theorem B. So it says that I'll just recall what Ziquan stated. So Theorem B just says that suppose I have, again, V is let's say an LC place of a complement. Then I have the following. So the graded ring of V is finitely generated, and I require that the degeneration is the KLT. So this will be the condition we want to provide the optimal degeneration. So this is if and only if my V is so-called monomial LC place of a special complement. So in other words, this will be the final finite generation statement that we want to prove. But certainly this tells us that the finite generation is equivalent to or implied by valuation being a monomial LC place of special complement. But we started with valuation being a delta minimizer, right? A valuation computing this infimum of log discrepancy divided by the S invariant. So we want to also set up the bridge that any delta minimizer is a special complement, is a monomial LC place of a special complement. So, but before, let me just remark that this is indeed the technical core of the whole proof. So the most technical part appears in the proof of Theorem B. But before we focus on the proof of Theorem B, let me first focus on the part where a delta minimizer is always a monomial LC place of a special complement. So you have a lot of flexibility in choosing the complement. So this is so-called Theorem C. Which says that any, okay, so assume that delta X is at most 1, and this is computed by a valuation V, then that V is always a monomial LC place of a special complement. Okay, so then you can see that by putting together Theorem B plus Theorem C, this just tells us that any valuation computing delta at most 1 has a finitely generated radial algebra. So this implies the higher rank finite generation. Okay, so we will give a proof of Theorem C first, and then we will turn our focus on the technical core of Theorem B. Any questions? Okay, so let me continue. So the idea of Theorem C is again, you want to use this fact that delta invariant is approximated by this so-called delta M invariant coming from log canonical threshold of M basis type divisors. And last time Ziquan introduced this concept called the compatible divisors, which give us a way to increase the flexibility of your complements or divisors close to complements. And this will be the key points to show that any delta minimizer, you can actually just increase the flexibility of the complement. So it contains a fixed multiple of arbitrary anti-canonical divisors. So again, we just start from D be any Q divisor in the anti-canonical Q anti-canonical linear system. Then our goal is to show that there always exists a Q complement gamma, which is bigger or equal to some alpha 0 D. So this is a Q complement such that V belongs to its LC place, where my alpha 0 only depends on the delta invariant. And later you will see that my alpha 0 can be chosen as something like delta over n+1 minus epsilon. Okay, so therefore, if we can achieve this goal, then this tells you that the complement can always contain a fixed multiple of this divisor D, and you can choose D to be the push forward of your ample divisor G, and that shows that your gamma is indeed a special complement. Okay, so how do we achieve this goal? Is to use compatible divisors. So using compatible divisors, we can find, so there exists the M basis type divisor. Dm that is compatible with both the divisor D and my delta minimizer V. So this means that I can put as many multiples as I can of my divisor D into Dm. Meanwhile, I can also make sure that my Dm is sort of concentrated at the valuation V, or the center or the ideals of my valuation V. So this is a very, very nice trick, very useful trick. And the consequence of compatibility is that Dm will be bigger than or equal to, but this is, let me just put a footnote, this is asymptotically as m go to infinity, 1 over n+1 D, where this 1 over n+1 is actually the S invariant of the divisor D. So you can think about being compatible just means that I can, when I choose the basis, I first choose okay, so probably the first divisor I choose will be just the divisor D, and then I go to, you know, smaller and smaller orders, but I want to put as many Ds as I can. So eventually you can put this many Ds. And also, I know that my V evaluate on this M basis type divisor is also maximal because of compatibility. So this is precisely the S invariant at level M of my valuation V, and this converges to the S invariant of V as M go to infinity. Okay, so then I will use this M to serve as some auxiliary divisors to extract my valuation V or some rational perturbation of them. So hence I know that X delta M dm, this is by definition, is log canonical. But meanwhile, if I look at the log canonical threshold of this pair, sorry, so delta M dm of this valuation V, so this is precisely the log discrepancy of V minus the vanishing of dm times with delta m. But you know that that my V of dm is precisely the S invariant, Sm invariant of V. So this is equal to Ax V minus delta m times Sm of V. And then this actually converge to Ax V minus delta times S invariant of V, and this is equal to 0. So basically, this follows from the choice of V being delta minimizer, and also this m basis type divisor compatible with V. Okay, so now you have a sequence of log canonical pairs, and you know that delta is at most of 1, so therefore delta m, if I multiply this 1 minus epsilon, then this will be less than 1 for m very large. So therefore your pair, if I look at this pair, so x 1 minus epsilon delta m dm, so this is log Fano. And because my epsilon here chosen very small, I can always assume that A of x 1 minus epsilon delta m dm. So this log Fano pair, if I look at the log discrepancy of V with respect to this pair, so this actually KLT, you can make sure that this is less than 1 or less than some small coefficient, or maybe indeed can be very small. Okay, so therefore I can use BCHM to extract a model of my valuation V. So I use BCHM to extract a model where V is monomial. And this model, meanwhile, because I put this assumption that the log discrepancy is smaller than 1, but actually it can be very small as epsilon goes smaller and smaller, it actually converges to 0. Then you can also lift out the complement where your valuation V or the perturbation is almost an LC place. So therefore, then I use the global ACC by Yuchen, Liu, and Xu. I can actually show that that there exists this complement gamma, Q complement on X, such that my V is an LC place of this Q complement. So you can think about this gamma as some kind of limit of this delta m dm, and then maybe plus some general divisor, so that it's asymptotically anti-canonical. And then my V is an LC place, and at the same time I can make sure, because my delta m, you see, sorry, my dm here is asymptotically bigger than this guy. I can assume that my gamma is asymptotically bigger, and actually by taking the limit, I can make sure it's actually bigger than delta over n plus 1 minus epsilon times my divisor d. Okay, so therefore you see that using compatible divisors, I can actually concentrate my m basis type divisor along every prescribed anti-canonical divisor d, such that V is still an LC place. So therefore, if we just choose D to be bigger than some push forward of some general ample divisor on Y, this tells us tells us that this gamma is indeed a special complement. Okay, so this gives us the proof of theorem C. Okay, any questions? Okay, so now you see that every delta minimizer is actually a monomial LC place of special complement, and actually this kind of LC place of special complement not only applies to delta minimizers, but also applies to some other minimizers appear in other functionals in K-stability theory. I think later on, Harold will give a talk on the joint work with myself, Chenyang and Ziquan, where we apply this same technique to the so-called H functional. And that will also produce like a higher rank finite generation result for valuations computing the so-called H functional. And that's related to certain Kähler-Einstein soliton degeneration of Fano variety. But then, since we have proved the theorem C, the only missing step is the proof of theorem B, and we will focus on that. So here our assumption will be that my valuation V is a monomial LC place of a special complement, and I want to prove that the graded ring is finite generated, or in other words, you just need to prove that the alpha invariant. So we go here. You just want to prove that the alpha invariant of the perturbation, little perturbation, is bigger or equal to some fixed constant alpha 0. So let me state. So now we go to proof of theorem B. So again, our assumption is suppose my valuation V is so-called monomial LC place of a Q complement or special complement gamma. With respect to this pair YE, which is a log resolution to X. So let's just recall, this just means that I can find an ample divisor G, effective ample Y, such that the pullback or the straight transform of gamma is bigger or equal to G. And also I assume G avoids the center of V on Y. Okay, so then our goal is to show that that I can actually perturb my valuation V in this quasi-monomial valuation space. So there exists a neighborhood U of alpha. So my V is V alpha in the space. So R in this quasi-monomial valuation space. And also I want that there exists some constant alpha 0 such that for any beta in this neighborhood and at the same time a rational vector, I can find, okay, so before that, I also want to fix any divisor D in the Q linear system of minus Kx. I can find a complement. Maybe I call it a gamma prime, such that the following hold. So the first condition is I want my gamma prime to be bigger or equal to alpha 0 d, right? And secondly, I want my V beta is an LC place of X gamma prime. Okay, so you see that this is like incorporate what we have from the lemma where I show that alpha invariant of the central fiber is bigger or equal to alpha 0 is equivalent to finding a complement bigger than alpha 0 times any anti-canonical divisor, such that the LC place still contain the prescribed valuation. So you can see that this is some kind of this should be interpreted as some kind of perturbation argument, because I start from some complement gamma where my V is an LC place, and you know that the LC places of any log canonical pair is a form a dual complex, right? So therefore, there certainly exists a fixed polytope neighborhood of alpha, such that any vector in this polytope is still an LC place of gamma. And then you just want to perturb gamma a little bit, so that for every rational point in a smaller neighborhood, this prescribed vector beta becomes the only LC place. And meanwhile, you also want to increase this divisor D inside it. So there are actually two steps or two tricks that goes into finding this new complement gamma prime. Okay. Any questions? Okay, good. So next, I want to just first extract this divisor, this valuation beta, because I know that my beta will be coming from some weighted blowup of the log resolution y. So I just choose, so let rho C f to y be the weighted blowup, and actually beta weighted blowup. Extracting divisor f such that the order of vanishing of this divisor is proportional to V of beta. Okay, so now I basically just transform my V beta as some kind of weighted exceptional divisor of weighted blowup, or geometrically this will be like a weighted projective space bundle over the center. Okay, and then what I'm going to do is I will make this assumption, and I call it assumption star. So this is some key assumption which comes into finding this new complement gamma prime, and the assumption here goes as follows. Let me see. So what I want is I want two positive constant A and B, such that first of all, if I look at the log canonical threshold of F and some different divisor phi, and then some linear series L, so I will explain later, I want this to be bigger than A. And at the same time, I want the Sashadri constant of the divisor G with respect to this log discrepancy times my divisor is bigger than B. So let me explain what they are. All right. So here, my L is the pullback of kx and then minus axf times f. So L is something coming from pulling back an anti-canonical divisor and then do some restriction. And then my phi is like a different divisor. So phi is the pullback of kx. So kx, and then okay, so maybe I rewrite this. So I pull back kx to this this model z. I get something like kz plus delta z, and my phi is something obtained by doing a junction. And then I just increase the coefficient of f, and then there may also be a zero. So I want to take the positive part, and I restrict to f. So this will be my kf plus phi. And then this Sarshadri constant is just a maximal number, the sup of all t, such that the pullback of g minus t times this constant times f is f. Okay, so this seems a little bit technical, but the idea will be something like this. So first of all, this Sarshadri constant just means that my divisor g, is ample on y, and I form this weighted blowup, which is, it's like a Kähler component, but maybe with a bigger center than point, possibly. Then you know that your divisor f as an exceptional divisor is anti-ample on this weighted blowup. So therefore, if I can shrink my divisor g after pullback, subtracting some multiple of f, then I can concentrate. I can find the divisor which is concentrate at certain level on my divisor f. So in order to find this gamma prime, so that f is again some LC place, you want to sort of concentrate your divisor along this weighted blowup. So the Sarshadri constant is used to concentrate. On f, and this log canonical threshold is used to do inversion of a junction. So in the end, we want to prove something is log canonical, where my f is the only LC place. So what we do is we find some pair which is, after you restrict to f, it is log canonical or even PLT, and then you use inversion of a junction to show that it is actually PLT in a neighborhood of f, and then you use some kind of Kähler-Shortgrove connectedness to show that this pair is indeed a PLT and f is the only LC place. Okay, so we assume these two assumptions on the alpha invariant type argument type estimate and the Sarshadri constant type estimate. So these two estimates will be enough to make sure that I can find such a divisor gamma prime. Okay, so the first reduction, I think I don't have enough time to go into details. But the first reduction we did is enough to assume that the divisor D you choose, which is presumably any anti-canonical divisor, but you wanted to have a fixed vanishing order. So you want V of D, or let's say V beta. So V beta of D equals the log discrepancy of V beta. Okay, so with this first reduction, what we're going to do is we'll look at the following. So we consider the pair. Wait a second. Consider this guy here. Okay, so rho upper star G minus let me see, because my Shadri constant is bigger than B, this just means that this guy here is ample, right? So this guy is ample, and I can find a general divisor A, H prime. So this is a general divisor, which serves as the purpose of concentrating on F. And then I let my H to be the push forward of this new divisor H prime, which is indeed the Q linearly equivalent to G. Okay, so what I will do is I will replace the G by H in my complement gamma. And because my H prime, you can see that it subtracts this amount of F. So this means that if I replace my gamma by gamma minus the push forward of G plus the push forward of H, then you see that nothing changed, but the order of F increased. Then the order of F increased, and nothing else changed. So this is like a tie-break argument where essentially you know that F is PLT on some model, then you just increase the order of vanishing along that point, along that divisor, and all the other remain the same. So therefore, you have some divisor which is not log canonical anymore, but the only bad divisor is this divisor F. And on the other hand, I know that from this log canonical threshold bound, I can actually look at this pair. So delta y is some Kraepelin pullback, and then plus A times the pullback of D, and then plus some multiple of this general ample divisor. So this is log canonical near the center of F, and F is the only LC place. So here, in order for this contribution of F to be precisely the log discrepancy, you want to put C to be something like 1 minus A over B. So this follows from some computation. Okay, so in the end, what we're going to do is we will just combine this divisor here with the other divisor, so y delta y plus gamma minus pi over star g. So we will do like a convex combination. So we'll denote this divisor by b, which is t times a pi over star d plus ch, and then plus 1 minus t of this complement minus the divisor g. So where in order for this to come from something pullback on x, I require this t to be 1 over 1 plus c. So then I can actually rewrite this b as at times pi upper star d, and then plus 1 minus t times this divisor where I said it has more concentration on the divisor f, but remains KLT otherwise. Okay, so then you can check that the pair y delta y plus b is sublog canonical near f, and f is the only LC center or LC place. Okay, so moreover, you can see that y delta y plus b is Kraepelin pullback of the pair x and then you have AT times D, and then plus 1 minus T gamma minus the contribution of G plus this new contribution H. Okay, so this whole thing here, I will call it the gamma 1. And by checking the class of gamma 1, you can see that gamma 1 is actually smaller than minus kx. So which means this pair is log Fano. And at the same time, x gamma 1 is sub, or I don't need sub now. So it's log canonical near F, or the center of F, and F is the only LC place. So now you have a log Fano pair, which is log canonical near the center of some divisor, and the divisor is the only LC place in its neighborhood. Then you can apply the Kähler-Einstein connectedness to say that this pair is actually indeed log canonical. So then by Kähler-Einstein, connectedness, we know that x gamma 1 is indeed log canonical with F as the only LC place. Okay, then you can just add in some extra, ample divisor. So gamma 1 plus an ample divisor, general ample divisor to be. So this is the desired special, or let's say this is a desired complement where my gamma prime is bigger or equal to AT times D. So D here is some arbitrary divisor start with, and secondly, F is an LC place of X gamma prime. And then you just need to, what's left is just you need to verify this assumption star. But okay, so first of all, I don't have time to discuss them, but at the same time, their proof is also not very hard. Because it splits into two statements, right? The first one, you want to bound certain alpha invariant type estimate on the exceptional divisor of this weighted blowup. But you know the weighted blowup is like a weighted projective space bundle over the center. So therefore, essentially, you have a big torus action on the fiber, and you can sort of reduce the log canonical threshold computations to the like toric boundaries in some sense, and you can get that estimate. On the other hand, you want to estimate the Sashadri constant, where essentially boils down to some global generation argument, and you can use certain vanishing theorems to prove that. So in the end, we get assumption star, and then this argument just goes. Okay, I guess I'm maybe 4 minutes over time, so let me stop here.
Thank you very much, Yuchen. Does anybody have a quick question for Yuchen?
So if we look at special dividers close to minimizer in the sense of A over S, not necessarily near the minimizer in the dual complex. So can we bound the alpha invariant of the induced central fibers?
Yeah, good question. So if you have a special divisor, or even a weakly special divisor whose A over S is close to delta, then I think it must be a LC place of a bounded complement. So essentially the dual complex is bounded. Then I think it must be a perturbation of delta minimizer in the neighborhood. But on the other hand, it might happen that your delta minimizer generates a smaller rational linear span. So in that case, I'm not sure. But if your delta minimizer has the maximal, generate the maximal like neighborhood, then I think you can bound alpha.
Any other question? If not, then let's thank you, Chen, again, and I hope to see you all back next Monday.
One quick announcement, sorry.
Yes.
Just like to encourage anyone who is interested in presenting a poster and who hasn't registered to do so, we still definitely have some spots left. So that's next Thursday, I believe.
Yeah, so as the final speaker of the lecture series, let's thank the organizers for this wonderful opportunity.